It seems I am still alive, so I should tell you about the first problem. It's simple and fun. Before this video, or around 6 months ago, I actually tried to solve this problem, but I ended up not solving it. After 5 months though, I figured out an idea to solve it, and that idea led me to create this blog. Now, I'll be discussing possible solutions for this question, so spoilers ahead if you want to solve it yourself. I'll link the website in the description if you're interested. You're still here. Alright, here's problem 1. 3, 5, 6, and 9 are multiples of 3 or 5 below 10. If we were to add them all up, we would get 23. It's not a really big number as detected by my big number detector. That's cool, but here's the thing. What is the sum of all multiples of 3 or 5 below 1,000? 1,000 is kind of a big number, and by my expectations, bigger numbers require larger solutions. For instance, a possible way to solve this manually is to list down all multiples of 3 or 5 and add them as a list. That method takes a lot of time and not to mention has a significant margin of error. So how do we not waste time? We rely on computers. These questions are designed to be solved using computers because we simply don't have enough time to solve it with our heads. I will present 3 solutions ordered by least efficient to most efficient. The first one might use strings. You've probably learned in class that a number is divisible by 3 if the sum of its digits is a multiple of 3. A number is divisible by 5 if the ones digit is a 5 or a 0. These divisibility rules will be the basis for our algorithm if a number is a multiple of 3 or 5. For an example, we will use 475. Let's start with an easier one which is divisible by 5. The ones digit is a 5, so it's obvious it's divisible by 5. For divisible by 3, we add its digits and then add the digits again until it's a single digit number. This single digit number is known as a digital root, and I learned about it from a certain visual novel. The digital root is not divisible by 3, so the number itself is also not divisible by 3. Now that we solve for such, we now determine if this number is part of the final answer. As long as it is divisible by 3 or 5, the number is part of the sum. We're going to tell the computer to do this for all numbers below 1,000. Here's how the computer would do it. 1, no. 2, no. 3, yes. 4, no. 5, yes. 6, yes. Eventually, we will get to the answer as n approaches 999. Even so, I don't recommend this solution, considering there's a lot of computation for 999 numbers, especially when checking if a number is divisible by 3. So how do we reduce more computations? Simple, we don't use divisibility rules. We instead use the modulo operator. It yields a remainder of a division known as a modulus. Let's say 6 divided by 4. We know the answer is 1.5, or 1 with a remainder of 2. 6 mod 4 should then be the remainder, which is 2. Here's another one. 9 mod 3 is 0 because 3 is a factor of 9. If a mod b equals 0, then a is a multiple of b. Let's go back to 475. 475 mod 3 is equal to 1, which means it's not divisible. 475 mod 5 is equal to 0, which means it is divisible. We then look if at least one of the conditions is true, and if there is, then that number is part of the sum. We then tell the computer to do this for all numbers under 1000. We can see its results with the results table 2.0, and hey, it's already doing all the work for us. Again, it would get to our answers as n approaches 999. Unlike the first solution, this is a generally accepted answer. But did you know there's a way to solve this without iteration? Let's look at the third solution and begin it with defining a function. Sum of multiples with parameter b. It will return the sum of the integers that are multiples of b and are lesser than 1000, where b is an integer. In future references, it will be called sb. We will be using this function to get our answer. The function calculates the sum using the arithmetic series formula over here. N is the number of terms and can be solved by dividing 999 with b and then flooring the value. A sub 1 is the first term and a sub n is the last term or the nth term. If b were to be equal to 3, then n is equal to 333. A sub 1 will be equal to 3 because 3 is the first multiple of 3. A sub n is the 333rd multiple, which should be 999. We then evaluate the numerator, then divide it by 2 to get 166,833. Wow, that's big. Should the final answer be equal to S3 plus S5? Nope. As we can observe here in both sums, the number 15 appears twice. Note that 15 is the least common multiple of 3 and 5. We need to subtract it with the multiples of 15. This will result in our final answer. If we simply add S3 and S5, multiples of 15 will be counted twice because they belong in both sets. We simply subtracted by S15 to reduce the repeated numbers. This is known as the inclusion-exclusion principle, which is studied in set theory. In conclusion, math is cool.